My name is Kelly Mercado, and in this video, I will present the world's first carbon nanotube computer. A team of engineers from Stanford, led by Subhasi Mitra and Philip Wong, successfully built a computer whose central processor is based entirely on carbon nanotubes, a form of carbon with remarkable strength and conductivity. The computer is currently slow and simple compared to the processors we have today. Nonetheless, its creators showed that carbon nanotube electronics are a viable potential replacement for silicon. Once perfected and scaled to industrial levels, the creators are expecting to launch devices which will run at increasingly faster rates, require less energy, and remain cool, completely surpassing the capabilities of today's silicon-based processors. Creating transistors with enough carbon nanotubes to carry a sizable amount of current has proved to be very difficult. Engineers face two main issues when trying to make them work exactly the way they needed to. Growing carbon nanotubes can result in a mix of metallic and semiconducting forms, which is undesirable. These metallic forms perpetually conduct electricity instead of acting like proper semiconductors, which can be switched off. Moreover, some nanotubes may not grow in accordance to the uniform alignment required by the engineers. The Stanford team solved the metallic nanotube problem by designing circuits that could vaporize metallic tubes, leaving only the semiconducting ones behind. To fix the misaligned tubes, the researchers developed a computer program capable of mapping out a circuit layout to determine how to overcome misalignment. In addition to these solutions, the researchers have refined the fabrication process to increase the number of carbon nanotubes while preserving uniformity. Their fabrication process begins with quartz on which the carbon nanotubes are grown. The nanotubes are then transferred over to a target surface to make the transistors. A glue-like polymer is used to prevent the carbon nanotubes from sticking to one another. With this approach, the team was able to make transistors with an average density of 100 carbon nanotubes per micrometer. With these problems solved, the research team was able to create a basic computer which can perform tasks like counting and number sorting. It supports a basic operating system that allows it to switch between these two tasks. It can also run MIPS, a commercial instruction set designed back in the 1980s, allowing it to run over 20 different instructions. The nanotube processor has 10 million times fewer transistors on it than today's typical microprocessors, making it run much more slowly and operate at 5 times the voltage, using about 25 times as much power. Bringing the carbon nanotube computers into mass production is currently not feasible. With the tools at hand, the Stanford group can't make transistors smaller than about 1 micrometer. This size reduction should be possible since previous work at the International Business Machines Corporation, or IBM, has shown carbon nanotube transistors with channel lengths smaller than 10 nanometers. Ultimately, the researchers want to make computers with thousands of smaller transistors and could run faster. To reach the excellent level of performance theoretically offered by the nanotubes, the device and materials experts at IBM plan to start working in closer collaboration with the circuit designers at Stanford. In relation to this approach, let's look at a patent of fabricating carbon nanotube transistor devices created by Thomas Tumbler and Brian Lim for Atomate Corporation. This approach involves a porous alumina template with numerous parallel pores used to hold the single-walled carbon nanotubes. The template is produced by anodizing the alumina substrate. This template, having pores, is exposed to a hard hydrocarbon gas at a certain temperature to grow carbon nanotubes in the pores. An insulator layer and 2 gate electrodes are formed, wherein between these electrodes are at least 2 carbon nanotubes in the template.